This is part 2 of a series on K-means clustering. In this video, we will implement K-means clustering from scratch. This video was produced in Korean and translated into English. My voice was generated by AI, text-to-speech. In the last video, we looked at the basic algorithm of K-means. In this video, we will implement this algorithm from scratch. And let's also implement it using the Scikit-learn's K-means class. Before writing the code, let's look at how to calculate the distances using the matrix broadcasting. Given 5 training data points and 3 centroids, we want to generate a distance matrix for all combinations. Of course, you can use multiple for loops to calculate the distances one by one. However, the matrix broadcasting makes it easier and faster to get the distance matrix. Now let's look at how the matrix broadcasting works. There are 5 training data points X and 1 centroid C. To easily understand the matrix broadcasting, let's consider only one centroid. X is a 5-row 2-column matrix, and C is a 1-row 2-column matrix. Let's calculate X minus C. At first glance, it may seem that X minus C cannot be calculated, because the 2 matrices have different shapes, but it can be calculated through matrix broadcasting. The upper vector is broadcast downwards, and then X minus C is computed. The difference between this vector and this vector is computed. And the difference between this vector and this vector is computed. The results are 5 rows and 2 columns. Let's create a simple rule here. If the numbers of columns are the same, and the number of rows on one side is 1, broadcasting occurs in the row direction as many as the number of rows on the other side. The number of rows on one side must be 1. If it is 2 or 3, no broadcasting will occur. And X minus C cannot be calculated. Now let's calculate the distances in this case. There is not just one, but multiple centroids. In this case, the broadcasting is a bit more complicated. We want to calculate all the distances between the training data points and their centroids. To create a distance matrix like this, the first subscript in D represents a centroid number, and the second subscript represents a data point number. For example, this element represents the distance between the third centroid and the first data point. This is the distance, D31. A total of 15 distances need to be calculated this way. The shape of the distance matrix is 3 rows and 5 columns. Calculating X minus C requires broadcasting. To do this, we need to convert this matrix into a 3-dimensional array. Add a DO axis to the matrix X, and a D1 axis to the matrix C. If you draw the converted 3D array, it will look like this. The data points 1, 2, and 0, 1, etc. are on the D1 and D2 axes like this. And we add a new axis D0 to enable broadcasting in D0 direction. For matrix C, we add a new axis D1 to enable broadcasting in D1 direction. The centroids, 1, 1 and 0, 0, etc., are on the D0 and D2 axes like this. Then the shape of the 3D array X becomes like this. And the shape of the 3D array C becomes like this. Now let's calculate X minus C. Let's apply the rule we created on the left. The last dimensions are equal, and this dimension is 1, so it increases to 3 through broadcasting. And since this dimension is also 1, it increases to 5 through broadcasting. Then their shapes will be the same. Therefore, X minus C can be calculated. The result is a three-dimensional array, 3, 5, 2. This is the result of X minus C. Now let's calculate the Euclidean distance between the first training data point, 1, 2, and the first centroid, 1, 1. The distance can be calculated like this. This part in the parentheses is X minus C. Taking the square root of the sum of squares of X minus C gives us the distance. Since we are summing along the D2 axis, the last dimension is gone. So the final result will be a 3-row, 5-column matrix. This is the distance matrix at the top right we wanted to find. Next, let's write a Python code to find the distance matrix using this method. Add a D0 axis to the data matrix X, and add a D1 axis to the centroid matrix C. Taking the square root of the sum of squares of X minus C gives us the distance matrix. This is the distance matrix with 3 rows and 5 columns on the top right corner. Broadcasting makes coding easier than using multiple for loops. Next, let's write code to generate the distance matrix using the broadcasting we just looked at. And then perform the KMeans clustering using that matrix. The data we will use is like this. Let's cluster this data into 3 groups. N is the number of data points, and K is the number of clusters. M is the number of iterations. That is, the number of times to update the centroids. L is the number of iterations to solve the local minimum problem. After repeating KMeans clustering L times, the one with the smallest error is finally selected. Create a function to visualize the training data points. We then write a function to color code and visualize the training data points and clustering results. Repeat KMeans clustering L times while changing the position of the initial centroids. Randomly select K training data points and use them as initial centroids. Next, update the centroids while repeating it M times. Calculate the distances between the training data points and the centroids. We calculate the distances using the matrix broadcasting seen on the previous page. Next, we assign each data point to its nearest centroid. If the variable assign is like this, it means that the first data point is assigned to cluster 0. And the second data point is assigned to cluster 1. Next, move the centroid to the average coordinates of the data points belonging to that cluster. Find the data points belonging to the centroid C. Then, we calculate the error to measure the clustering performance. We then calculate the average coordinates of these data points and use them as the new centroid. Update the existing centroid to the new centroid. To see the centroid updates during M iterations, you can run the following code. After repeating this process L times, the result with the smallest error is finally selected. Lastly, we visualize the clustering results and the error history measured over M iterations. We then check the cluster numbers assigned to each data point. The results are as follows. The data points were clustered into 3 groups as follows, and the error has been reduced significantly. The cluster numbers assigned to the data points are as follows. The first data point belongs to cluster 2, and the second data point belongs to cluster 1. The cluster numbers may vary from run to run. The cluster number itself is not important here. What's important is that the first, third, and fifth data points are in the same cluster, and the second, fourth, seventh, eighth, and ninth data points are in the same cluster. The data points belonging to the same cluster have the same properties. If your test data point falls into cluster 2, you can see that it is similar to the data points belonging to that cluster. Finding this out is the purpose of clustering. Let's run this code. The results are as follows. Let's run this part of the code to check for centroid updates during the training process. You can see centroids being updated like this. If you run this code multiple times, you may sometimes see local minimum problem. This time, we will implement this using Scikit-learn's KMeans class. The data we will use is the same as that used in the previous code. Create a KMeans model. Set the number of iterations the same as the previous code. The initial centroids are set randomly. Fit this model to the training data X. Since KMeans is an unsupervised learning model, the target Y value is not used in the fit function. The coordinates of the final centroids are in this variable, and the final error is contained this variable. Let's check the results. The data points have been clustered into 3 groups as shown below. The final error is 5.7561. This is quite similar to the error in the previous code. The reason this is not exactly the same is because the training data points were randomly generated. The cluster numbers assigned to each data point are contained in this variable. Let's run this code. The results are as follows. The final error is 5.6106. The cluster numbers assigned to each data point is as follows. So far, we have implemented KMeans clustering. In the next video, we will look at the KMeans++ algorithm, which can reduce the local minimum problem.